Hi, welcome to Sunil Maths tutorial, functional analysis class number 47. In this video, we learn one very important theorem. Let us see the statement. Every Hilbert space is reflexive. We are going to prove every Hilbert space is reflexive. One of the important theorem. Let us see. Let capital H be a Hilbert space and H double star is second conjugate space. Second conjugate space. H is a Hilbert space and H double star is a second conjugate space. We have to prove that this Hilbert space capital H is reflexive. We have to show that the Hilbert space is reflexive. To prove that Hilbert space is reflexive, it is equivalent to prove that. There exists a natural embedding. From capital H to second conjugate space H double star, and this natural embedding is an isometric isomorphism. Please observe that. Our aim is to show that H is reflexive. To prove that H is reflexive, it is equivalent to show that there is a natural embedding from H to, Hilbert space to second conjugate space, and the same natural embedding is an isometric isomorphism. So this is our aim. So let us take X be any fixed element of H. Let small x be any fixed element of the Hilbert space capital H, and capital Fx be a scalar valued function. Defined on the conjugate space. Defined on H star. Defined on the conjugate space H star. And defined by fx of f is equals to f of x. Fx of f is equals to f of x for every f belongs to conjugate space H star. So right, we are taking, see that x be a fixed element of the Hilbert space and fx be a scalar valued function defined on the conjugate space H star, defined by fx of f is equals to f of x for every f belongs to H star. So by previous theorem, we learn a theorem in Banach spaces. I write the complete statement of that theorem. By previous theorem, I write the complete statement of that theorem. Let capital N be a normed linear space, then each vector small x in capital N induces a functional capital Fx on n star defined by fx of f is equals to f of x for every f belongs to n star such that norm fx is equals to norm x. Further, it satisfies one more condition. Then the mapping capital J maps n into n double star defined by j of x is equals to fx for every x belongs to capital N, for every x belongs to capital N, gives an isometric, gives an isometric isomorphism, of capital N into n double star, This is previous theorem. I prove this theorem among one of the video either between 20s, video number 20 to 30 in between. So this is the theorem. Let us see the statement. N be a normed linear space. For each vector x in capital N, each vector x in capital N induces a functional fx defined on n star, defined by the same equation fx of f is equals to f of x for every f belongs to n star, satisfying the condition norm fx is equals to norm x. Then there must be a mapping J that maps from n into n double star, defined by j of x is equals to fx, gives an isometric isomorphism of capital N into n double star. So right, by applying this theorem to our present theorem, by applying this theorem to our present theorem, there must be a functional fx that belongs to second conjugate space H star, as well as thus for each vector x belongs to capital H gives rise to a functional fx in H double star. This is the main point here. By applying that previous theorem to our present theorem, for each and individual x belongs to H gives rises to a functional capital Fx in the double conjugate or second conjugate space H double star. And remember that here this fx called the functional on capital H star induced by the vector x, and also by applying the same theorem here, there be a mapping J that maps from H into H double star, defined by J of x is equals to fx for every x belongs to capital H. Then this J is an isometric isomorphism of capital H into H double star. So this is the complete application of our theorem from here to here. So remember that from here to here is the complete application of previous theorem. For each vector x belongs to capital H, it gives rise as a functional fx in H double star. Here fx is called the functional on H star induced by the vector x, and there is a mapping J that maps from H to H double star defined by J of x is equals to fx. Then this J is an isometric isomorphism of H into H double star. So right, we complete our proof. By showing that capital J is mapping of capital H onto H double star. This is important point. We conclude our proof by proving that H is a onto mapping. By proving H is a onto mapping. To prove that H is onto mapping, we define two functions. Define T1 that maps from H into H star, defined by the equation T1 of X is equals to Fx, where Fx of Y is equals to inner product of Y comma X for all Y belongs to capital H. And define one more mapping T2 that maps from conjugate space to second conjugate space H star to H double star, defined by the equation T2 of Fx is equals to capital F Fx, where capital F Fx is equals to inner product of F comma Fx for every F belongs to H star. So our aim is to prove that J mapping is onto. So to prove that J is onto, we define two different mappings, T1 and T2. T1 is from H to H star, T2 is from H star to H double star. Then obviously you observe that the composite mapping T2 circle T1 must maps from H to H double star. You please observe that T2 is defined from H star to H double star. T1 is defined from H to H star. Then the composite function T2 circle T1 that must maps H to H double star. Again here we use a previous theorem. So this is clearly just previous theorem, video number 46 I think. By previous theorem, I write the complete statement of previous theorem. There is a mapping pi that maps H into H star defined by pi of y is equals to Fy, where Fy of x is equals to inner product of x comma y is 1 1 onto additive but not linear and an isometry. This is the previous theorem. This theorem proved in video number 46 I think. So by applying this theorem to our present theorem, by applying this theorem to our present theorem, we conclude that T2 circle T1 that maps from H to H double star is same as the natural embedding capital J. It means T2 circle T1 is same as the mapping J. Finally, we conclude our proof. We show that J is equals to T2 circle T1. To prove that, consider a term T2 circle T1 of x is equals to T2 of T1 of x. What is by our definition of T1 of x? Here it is. T1 of x is equals to Fx and Fx of y is equals to inner product of y comma x. So T2 of T1 of x, this is nothing but T2 of Fx. By the definition of T2, it can be written as f of capital F Fx. You see here, this is T2 definition. T2 of Fx is equals to capital F Fx. Capital F Fx is equals to, this can be written as inner product of f comma Fx. Again it can be written as inner product of Fy comma Fx, because this f is equals to Fy by previous theorem. So inner product of Fy comma Fx is equals to, you can write inner product of x comma y. To understand these two steps, you must watch video number 46, inner product of x comma y. Inner product of x comma y can be written as Fy of x. This Fy of x is nothing but f of x. This is nothing but capital F of This is nothing but capital F of capital Fx of f. Capital Fx of f. So this is nothing but j of x. I complete write the derivation part. Please observe this carefully. T2 circle T1 of x is equals to T2 circle T1 of x is equals to T2 of T1 of x. By definition of T1 of x, it can be written as fx. By definition of T2, it can be written as capital F fx. By definition of capital F, it can be written as inner product of f comma fx. And f is equals to fy. So inner product of fy comma fx. So it can be written as inner product of x comma y. This is nothing but inner product of, fy of x, f of x, simply fx of f, which is nothing but j of x. So this proof concludes as T2 circle T1 of x is equals to j of x. Therefore, we conclude that T2 circle T1 is equals to j. Both the mappings are same. So already this is onto function. T2 circle T1 is an onto. Therefore, j is also onto. Therefore, j is onto. Onto mapping of Hilbert space capital H into second conjugate space H double star. This condition shows as capital H is reflexive. Capital H is reflexive. What it means? Every Hilbert space is reflexive. Every Hilbert space is reflexive. That's it. This completes the proof. One of the important theorem, I simply repeat the theorem. Please observe that in this theorem we use two previous theorems. So if you know the previous theorems, if you are aware of previous theorems, then this theorem is very simple and easy. So just I revise the theorem, I revise the terms. Please observe that our statement is every Hilbert space is reflexive. Let H be a Hilbert space. H double star be the second conjugate space. Our aim is to show that we have to prove that H is reflexive. To prove that H is reflexive, it is equivalent to prove that there is a natural embedding from H to H double star, and the same natural embedding must be an isometric isomorphism. To prove this, let us take x be a fixed element of the Hilbert space and fx be the scalar valued function in H star defined by fx of f is equals to f of x for every f belongs to H star. There is a previous theorem. I write the complete statement. N is a natural normal linear space. Then for each x in capital N, we have a functional fx on n star defined by fx of f is equals to f of x. Then there is a mapping j that maps from n into n double star defined by j of x is equals to fx. This mapping j gives isometric isomorphism of capital N into n double star. If you apply the same previous theorem to our present theorem, for each vector x belongs to capital H, there is a functional fx in H double star, and this fx is called functional on H star induced by the vector x, and there is a mapping j that from H into H double star defined by j of x is equals to fx. And this j is an isometric isomorphism of H into H star. Now we complete our proof by showing that the mapping j is onto. To prove that it is onto, we define two functions t1 and t2. t1 by fx, where fx is equals to inner product of y comma x. t2 by capital F of fx, it is also inner product of f comma fx. Now it is very simple. You observe that t1 is mapped from H to H star and t2 is mapped from H star to H double star. Therefore, obviously t2 circle t1 is mapped from H to H double star. So again there is a previous theorem pi that maps from H to H star defined by pi of y is equals to fy, where fy of x is equals to inner product of x comma y is 1 onto additive but not linear and an isometry. Applying the same theorem to our theorem, this composite function is from H to H double star is a natural embedding same as capital J. It means T2 circle T1 and J has same properties. So we complete our proof by showing that T2 circle T1 is equals to J. So I think you understand this derivation part already. So T2 circle T1 of X is equals to J of X. Therefore J is onto mapping of H into H double star. Therefore H is reflexive. What it means? Every Hilbert space is reflexive. That's it. This completes the proof of our theorem.